Good evening, students. I hope you all are fine. So, in today's class, we will see Module 5 with respect to earthquake resistant structures. So, what are the things we will study in Module 5? Starting with seismic response control concepts. Next is seismic demand and seismic capacity. Next is overview of linear and non-linear procedures of seismic analysis. Next is performance-based seismic energy methodology. Lastly, seismic evaluation and retrofitting of structures. So, seismic analysis of RC buildings. The introduction part. Since earthquake forces are random in nature and unpredictable, the static and dynamic analysis of the structure have become the primary concern of civil engineers. So, what is happening? Since earthquake forces are random in nature, the earthquake forces are not static, they are random in nature and also unpredictable. You cannot predict at what time earthquake will occur. The static and dynamic analysis of the structure have become the primary concern of civil engineer. The main parameters of the seismic analysis of the structures are load carrying capacity, ductility, stiffness, damping, and mass. So, what are the main parameters of seismic analysis of structures? The main parameters of seismic analysis of structure are load carrying capacity, ductility, stiffness, damping, and mass. IS 1893-2002 is used to carry out the seismic analysis of multi-story building. So, as I said, you the standard code which is used for IS design over design of earthquake structure is IS 1893-2002. With the help of this, we will proceed. Seismic analysis of structure. The seismic analysis type that should be used for analysis depends upon external action, the behavior of structure or structural material, the type of structural model selected. So, what are the factors on which seismic analysis of structure depends? Number one, external action. Number two, the behavior of structure or structural materials. Number three, the type of structural model selected. On these three parameters, the seismic study depends. The different analysis procedure used are linear static analysis, non-linear static analysis, linear dynamic analysis, non-linear dynamic analysis. So the different analysis procedure used are linear static analysis, non-linear static analysis, linear dynamic analysis, and non-linear dynamic analysis. So in short, static analysis and dynamic analysis are there. Linear, non-linear, these are further cases. First is linear static analysis, also known as equivalent static method, based on the formula given in the code of practice. So what is the step? First, the design base shear is computed for the whole building. It is then distributed along the height of the building. The lateral forces at each floor level thus obtained are distributed to individual lateral load resisting elements. See here what we are trying to understand. In case of linear static method, it is also known as equivalent static method. This already we have seen in the module 3. So what is happening here? First, you will design the base shear for the whole building. It is then distributed along the height of the building. Next, the lateral force at each floor level, thus obtained are distributed to the individual lateral load resisting elements. Say the equivalent lateral shear force along two orthogonal axes. So this is a figure obtained from Springer. Next, what are the limitations of this method? The use of this method is restricted with respect to high seismic zones and height of the structure. High seismic zones and height of the structure. As a result of this, this can be considered as a limitation of it. High seismic zones and height of the structure. Next, the buildings have high modes of vibration than the fundamental mode. What is happening? The building have high modes of vibration than the fundamental mode. The structures have significant discontinuities in mass and stiffness along the height. The structure also have significant discontinuities in mass and stiffness along the height. So if you see here from IS 1893-2002 clause 7.5.3, the design base shear VEB is equal to AH into W. where W is the seismic weight of the building and AH is the horizontal seismic coefficient. So horizontal seismic coefficient AH can be calculated using IS 1893 Part 1 2002, which states that AH is equal to Z into I into SA 2D into R into J, provided that for any structure with T less than 0.1, the value of AH will not be taken less than Z by 2, whatever will be the value of IR. Z is the zone factor, I is the important factor, R is the response reduction factor, SA by G is the average response extinction coefficient, T is the undamped natural period of the structure. Zone factor. It is the indicator of the maximum seismic risk characterized by maximum considered earthquake MCE in the zone in which the structure is located. According to IS 1893 Part 1 2002, seismic zones are classified as 2, 3, 4, and 5 respectively. Average response acceleration coefficient SA by G. So it depends on the type of rock or soil site and also the natural period and damping of the structure. It is obtained from clause 6.45 IS 1893 2002. So it depends on the occupancy category of the building, and it is obtained from table 6 clause 6.4.2 IS 1893 2002. Site class is determined based on the average properties of the building within a certain depth 30 meters from the ground surface. Next, response reduction factor R. It is determined by the type of lateral load resisting system used. It is a measure of system's ability to accommodate earthquake loads and absorb energy without collapse. So what is response reduction factor? It is determined by the type of lateral load resistance system used. Different types of lateral load resistance system are there that we have already studied in the first module, base isolation system and all. So it is the measure of system's ability to accommodate earthquake loads and absorb energy without collapse. So what it is, a response reduction factor or lateral load resistance system, it is the ability of the structure to withstand earthquake loads and absorb the energy. And it is obtained from table 7 IS 1893 2002. Fundamental period. The approximate fundamental natural period of vibration TA of a MRF building from clause 7.0 without brick infill pans is equal to TA is equal to 0.075 H raised to 0.7 for RC building frame, and it is equal to 0.085 H raised to for steel building frame. With infill pans, T is equal to 0.09 under root D, where H is the height of building, D is the base dimension building at the plinth level. Vertical distribution of base shear to different floor levels. The lateral force induced at any level HI as per clause 7.7.1 IS 1893 2002 can be written by UI equal to VB into WI into HI square divided by summation of NG equal to 1 WJ head square, where QI is the design lateral force at floor I, WI is the seismic weight of floor I, HI is the height of floor I measured from the base, and is the N is the number of stories in the building, is the number of levels at which the master located. Horizontal distribution of base shear. The horizontal distribution of base shear as per FEMA P749 can be determined by Fij is equal to K into Ij summation of Nk equal to 1 K by K Fi, where Fij is equal to force acting on the lateral force resistance line J at a floor level I, and K is the number of lateral force resistance system lines. Kij and Kik is the storage stiffness of the lateral force resisting element line K and J at level I. Fi is the seismic force at floor level I. Drift storage. So what is drift storage? It is a measure of how much one floor or roof level displaces under the lateral force related to the floor level immediately below. So what is drift storage? It is a measure of how much one floor or roof level displaces under the lateral force relative to the floor level immediately below. It is the ratio of difference in deflection between two adjacent floors divided by the height of the story that separate the floor. Overturning moment and P delta effect. There is a tendency for the moment created by equivalent static force acting above the base to overturn the structure. The dead weight of the building is sufficient to resist the overturning force, but it must be checked always. So what is overturning moment and P delta effect? There is a tendency for the moment created by equal static force acting above the base to overturn the structure. क्या होता, देर आर चांसेस हैं कि इक्वल स्टैटिक फोर्स की वजह से जो बेस है वहां से ओवरटर्न हो सकता है स्ट्रक्चर. तो डेड वेट ऑफ द बिल्डिंग सफिशिएंट टू रेजिस्ट द ओवर फॉर, बट इसमें चेक, जो डेड वेट हम कंसिडर करते हैं बिल्डिंग डिजाइन करते रहे वो काफी है रेजिस्ट करने के वास्ते ओवर, बट उसको चेक करते रहना पीरियोडिकली। The stability coefficient for each story as per FEMA P71 can be calculated as theta equal to Pi delta I by Vi into Hi, where Pi is the weight of the structure above the story being evaluated, delta is the design story drift determined, Vi is the sum of lateral seismic design forces above the story, Hi is the story height. Now we will see what you mean by non-linear static analysis, also known as pushover analysis, used to estimate the strength and drift capacity of existing structure and the seismic demand for this structure subjected to selected earthquake. So non-linear static analysis, it is also known as pushover analysis, and it is also a famous type of analysis. It is used to estimate the strength and drift capacity of existing structure. So why it is used? It is used to estimate the strength and drift capacity of existing structure. How much is the drift capacity of the structure? Existing structure, that also is calculated by pushover analysis. And the seismic demand for this structure subjected to selected earthquake. It can be used for checking the adequacy of new structural design as well. It can be used for checking the adequacy of new structural design as well. It is an analysis in which a mathematical model incorporates the non-linear load deformation characteristics of individual components and elements of building, which shall be subjected to increasing lateral loads representing inertial forces in an earthquake until a target displacement is exceeded. See here, it is analysis in which a mathematical model incorporates the non-linear load deformation characteristics of individual components elements of the building, which shall be subjected to increase the lateral load representing inertial forces in an earthquake until a target displacement exceed. The response characteristics that can be obtained from pushover analysis are estimates of force and displaced capacities of the structure, sequence of failure elements and the consequent effect on the overall structural stability, identification of the critical regions where deformation inelastic deformations are expected to be high, and identification of strength irregularities of the building. So, what are the response characteristics that can be obtained from position analysis? Number one, it estimates the four estimates of force and displacement capacities of the structure. You can estimate how much is the force and displacement capacity. Next, sequence of failure elements and consequent effect on the overall structural stability. You will understand sequence of failure of elements and consequent effect on the overall structural safety. Identification of critical regions where the inelastic deformation are expected to be high, and identification of strength irregularities of the building. So all these are advantages of response. What we can say, a response characteristic procedure. So how it is done in pushover analysis, the magnitude of the lateral load is increased monolithically, maintaining a predefined distribution pattern along the height of the building. So how pushover analysis done? In pushover analysis, the magnitude of the lateral load is increased monolithically, maintaining a predefined distribution pattern along the height of the building. So the lateral load is increased gradually. Building is displaced till the control node reaches target displacement or building collapses. So how the building is displaced till the control node reaches the target displacement or building collapses. The sequence of cracking, plastic hinging, and failure of the structural component through the procedure is observed. The relation between base shear and control node displacement is plotted for all the pushover analysis. So if you see here, this is the building model and this is the pushover curve. This is the schematic representation of pushover analysis procedure. So pushover analysis may be carried out twice. First time till the collapse of the building to estimate target displacement. Next time till the target displacement to estimate the seismic demand. So pushover analysis consists of two parts. In the first time till the building collapse to estimate the target displacement. Next time till the target displacement to estimate the seismic demand. The seismic demand for the selected earthquakes are calculated at the target displacement level. So how the seismic demands are calculated? The seismic demand for the selected earthquake are calculated at the target displacement level. The seismic demand is then compared with the corresponding structural capacity to know what performance the structure will exhibit. So the seismic demand is then compared with the corresponding structural capacity to know what performance the structure will exhibit. Lateral load patterns. FEMA 356 suggests the use of at least two different patterns for all pushover analysis. So FEMA is 356 is a software which suggests the use of at least two different patterns for all pushover analysis. Group 1. In the group 1, code-based vertical distribution and lateral force used in equivalent static analysis. A vertical distribution proportion to the shape of the fundamental mode in the direction under consideration. A vertical distribution proportion to the story shape distribution calculated by combining modal responses from a response pattern analysis of the build. In the group 2, what is happening? A uniform distribution consisting of lateral force at each level proportion to the total mass of each level. An adaptive load distribution that changes as the structure is displayed. Now, target displacement is involved. Two approaches to calculate target displacement. First is displacement coefficient method, DCM of MR 356, capacity spectrum method, CSM of ATC 40. But of these approaches use pushover curve to calculate global displacement demand on the building. The only difference in these two methods is the technique used. Displacement coefficient method, FEMA 356. This method estimates the elastic displacement of an equivalent single degree of freedom system, assuming initial linear properties and damping for the ground motion excitation under consideration. So, what is happening in case of coefficient displacement coefficient method? This method estimates the elastic displacement of an equivalent single degree of freedom system, assuming initial linear properties and damping for the ground motion excitation under consideration. Then it estimates the total maximum inelastic displacement response for the building at roof by multiplying with the set of displacement coefficient. Capacity spectrum method. So what capacity spectrum method does? It uses the estimates of a ductility to calculate effective period and damping. This procedure uses the pushover curve in an acceleration displacement spectrum format. This can be obtained through simple conversion using the dynamic properties of the system. The pushover curve is in an ADRS format is termed as capacity spectrum for the structure. The seismic ground motion is represented by response spectrum in the same ADRS format is termed as demand spectrum. Now we will see what we mean by linear dynamic analysis. Response spectrum method is a linear dynamic analysis method. In this approach, multiple mode shapes on the building are taken into account. The spectrum method is a linear dynamic analysis method. So what is happening in this approach? Multiple mode shapes of the buildings are taken into account. For each mode, a response response spectrum method is linear dynamic. In this approach method, mode shapes of the buildings are taken into account. For each mode, a response is read from the design spectrum based on the modal frequency and the modal mass. They are then combined to provide an estimate of the total response of the structure using combination methods. Combination methods include the following: absolute sum method. Combination method include the following: absolute sum method, square root sum of square, complete quadratic equation. The design base shear VB is calculated using the dynamic If VB is less than VB bar, all the response comes to example. Force displacement storage shears and the base reaction should be multiplied by VB divided by VB bar. Buildings with plane irregularities and with vertical irregularities cannot be modeled for dynamic analysis by this method. For irregular buildings lesser than 40 meter in height in zone 2 and 3, dynamic analysis, though not mandatory, is recommended. So the model analysis equation is given by MK equal to summation of unequal load. Model analysis, the equation is this much. Mode shape coefficient at the floor I in the mode K. W is equal to seismic load of floor I. Design lateral force at each floor in each is equal Q I K equal to A K phi I K P K W I. The peak story VIK equal to summation of J equal to I plus 1 raised to N phi AK. Lateral force is stored due to all modes. The design lateral force F roof and F y at the roof is will be given by F roof is equal to V roof, Fy equal to Vi minus Vm. Modal combination. The peak response quantity should be combined as per the complete quadratic equation CKC method. R is equal to number of modes being considered. Rho Ig the cross model coefficient, lambda I response quantity in mode I, response quantity in mode J, model damping ratio, beta is frequency ratio. Square root sum of square method. Lambda equal to under root of summation k equal to 1 r lambda k, where lambda k is the absolute value of quantity in mode k and r is the number of modes being considered. Absolute sum method. If the building has a few closely spaced mode, the peak response lambda due to these modes should be obtained as lambda star is equal to summation of r on lambda naught. Non-linear dynamic analysis, also known as time history analysis. To perform such an analysis, a representative earthquake time history is required for a structure being evaluated. In this method, the mathematical model of the building is subjected to acceleration. To perform such an analysis, a representative earthquake time history is required for structure being evaluated. In this method, the mathematical model of the building is subjected to acceleration from earthquake record that represent the expected earthquake at the base of the structure. The method consists of a step-by-step direct integration over a time interval. The time history method is applicable to both elastic and inelastic analysis. In elastic analysis, the stiffness characteristics of the structure are assumed to be constant for the full duration of the earthquake. Whereas in the inelastic analysis, however, the stiffness is assumed to be constant throughout the incremental time only. Procedure. So what is the procedure? An earthquake record presenting the design earthquake is selected. The record is digitalized as a series of small intervals about 1 by 1 raised to 40 to 1 is to 25 second. A mathematical modeling of the building is set up, usually consists of lumped mass at each floor. The damping is considered proportional to the velocity in the computer formulation. The digitalized record is applied to the model as it accelerates at the base of the structure. The equation of motions are then investigated with the help of software program that gives a complete record of the acceleration, velocity, and displacement of each lumped mass at each interval. SAP 2000. It is a finite element based structural program for the analysis. Hello. हेलो बोलो रेडी है वो बाद में भी जाकर वो भी करे ठीक है शुक्रिया कब तक मिले रही दुकान ठीक है ठीक है It is a finite element based structural program for the analysis and design of civil structure. SAP 2000 is object based, meaning that the models are created using members that represent the physical reality. All the seismic analysis process can be analyzed effectively in SAP 2000. So what is SAP? It is a finite element-based structural program for the analysis and design of civil structure. SAP 2000 is object-based, meaning that the models are created using members that represent the physical reality. All the seismic analysis process can be analyzed effectively in SAP 2000. And overview, performance-based seismic energy methodology. So this is the ductile link analogy, original chain, ductile link, brittle links, loaded chain. So this is the ductile link stretched by yielding before breaking. This is the brittle link, do not ductile chain design. Demand and capacity. Design process. Structural design is the process of proportioning the structure to safely resist the applied forces in the most cost-effective and friendly manner. So this is the load effects requirement constraint design, member size and material specs reinforcement detail. So this is the loads and stress resultants. Loads often from analysis action depends upon the stiffness, deformation. This is the section capacity, section design process, the stress resultant stresses and strains. From serviceability to performance. Satisfying one design level does not ensure the other design levels will be satisfied. See here, from serviceability to performance. What it is saying, satisfying one design level does not ensure that the other design levels will be satisfied. ये जरूरी नहीं है कि अगर एक डिजाइन सेटिस्फाइंग हो तो दूसरी डिजाइन सेटिस्फाइंग नहीं. Serviceability design only ensures that the deflections and vibration etc. for service loads are within limit, but says nothing about strength. Strength design ensures that a certain factor of safety against overload is available within a number or a cross section, but says nothing about what happens if the load exceeds the design level. Performance design ensures that the structure as a whole reaches a specified demand level. Performance design can include both service as well as strength design level. The response design from loads to stresses, applied loads, building analysis, member action, cross section action, material sensor. From strains to response, material response, section response, member response, building response, load capacity. Lateral strength based design. This is the most common seismic design approach adopted nowadays. It is based on providing the structure with minimum lateral strength to resist seismic load, assuming that the structure will behave adequately in the nonlinear. For this reason, only some simple construction details are needed to be satisfied. Displacement based design. So what do you mean by displacement based design? It is in this method the structure is designed to pose adequate ductility so that it can dissipate energy by yielding and surviving the shock. This method operates directly with the deformation quantities, hence gives better insight on the expected performance of the structure. The displacement based design approach has been adopted by the seismic codes of many countries. Capacity based design. In this design approach, the structure are designed in such a way so that plastic hinges can form only in predominant position and in predetermined sequence. The concept of this method is to avoid brittle mode of failure. This is achieved by designing the brittle mode of failure to have higher strength than ductile modes. Energy-based design. This is the most promising and futuristic approach of earthquake design. In this approach, it is assumed that the total energy input is collectively registered by kinetic energy, the elastic strain energy and energy dissipated through plastic deformation and damping. Capacity design approach, general concept. What is capacity design? Capacity design is a design process in which it is decided which object within a structure will be permitted to yield ductile components and which object will remain elastic. So, based on capacity, this differentiation is done. Once ductile and brittle systems are decided upon, design procedure according to following guidelines. Ductile components. Ductile components are designed with sufficient deformation capacity such that they may satisfy displacement based demand capacity erosion. Brittle components are designed to achieve sufficient strength levels such that they may satisfy strength-based demand capacity ratio. Why capacity design? It is best to implement capacity design because structural elements is then a deliberate intention of the designer, not revealed in a secondary manner by computational tool. Further, because of the more many sources of uncertainty inherent to structural modeling analysis, unless ductile systems are predetermined, a computational tool may not accurately indicate which system will achieve inelastic response. In summary, capacity design enables the creation of more reliable computational method, which should lead to better structural design. It saves the computational time, pre-decide what is linear and what is non-linear. Capacity design philosophy. Structures are designed for many limit state. Load design is equal to all limit state must occur beyond a minimum load level. Capacity design equal to same as above, except now we choose that one limit state is occur before another. Difficult part is choosing the limit state that should govern. Where is capacity design used? Seismic design guideline. Seismic design guidelines UBC are written with a specific intent capacity. Special moment resistant phrase equal to hinges should form in a beam. Special concentric braced frame braces should yield in tension. Eccentric braced frame equal to link region of the beam in yield in shear. This already ductile link analogy we have seen. The beams must be weakest links and not the column. This can be achieved by appropriately sizing the members and providing correct amount of steel reinforcement in them. Strong column, weak beam design. Weak column, strong beam design is not preferred. Column should be strong. Two distinct designs of a building that result in different earthquake design. Strong column beam beams, weak column strong beams. Column should be strong. Next, buildings on flexible support shapeless. This technique is called base isolation. This already we have seen. View of basement in a hospital building, base isolator, basement wall supporting with base isolators, building some flexible supports, shakes lesser. This technique is called base isolation. This also we have seen. Seismic energy dissipation device, a device suitable for a suitable building, friction damper, viscous damper, welding damper, all we have seen. Lastly, uh, okay. Okay. So this completes our almost module 5. If you have any doubt or queries, you can just make a comment. Yes, in the comment box. If you have any doubts, you can mail me at nazimadgate@kevin.university. So I am ending the meeting. Thank you.